so we've just been building on what we've had before, and so now we get to actually put them together and go, when these two things join in a test tube or in a flask or something, then this is going to happen. So now what we're doing is we're breaking down exactly what is happening. Last week we were talking about the different types, the 5 different types of reactions that can form. So again, we're looking at chemical reactions. This is when something hasn't just changed shape. Physical changes are change shape, change phase, right? Solid, liquid, gas, but it doesn't actually change what the material is. So again, we are changing shape, we are combining atoms. They can be combined in what type of ways? They can be like magneted type together, and that's called what type of bond? An ion, I heard it. Okay, they can actually join and become a whole new molecule, and that was called a covalent bond. We had hydrogen bonds, which determine different ways that water, things with water and hydrogen move, and then we had metallics, but we've mostly worked on ionic bonds. You're just joining them together only because of what? What joins them? Polarity or the charges. Excellent. So the charges are what keeps it together, because it's like a magnet. One's negative, one's positive. They're sticking together. And then we're looking at covalent, where they're actually grouped in a lot more together. Okay? So let's re-go over. We ended on these types of reactions. We're going to re-go over them. The first one we had calcium plus 2 hydrochlorides. And we got calcium chloride and hydrogen. So that was I don't know if that's big enough for you guys to see. We replaced one of them, so that was called a single replacement. Excellent. Then we have carbon and hydrogen, so 2 separate things, and they just join together. That was called synthesis. So can you ever have synthesis with one element on the left side? No. Because synthesis, by definition, means the joining of 2 things. Okay? So you can never have synthesis if there's just one element there on the left side. Okay? Then we have carbon and hydrogen here. So we have, and it's 3 and 8, so it would be, tricarbon octahydroxide there. And then oxygen. And we've got this over here. But we ended up with carbon dioxide and water. So what type of reaction was that? Combustion. So what is the thing that you're looking for a combustion reaction? Oxygen and water. Most likely it's going to end up producing water on the other side, right? So we've got hydrochloride and potassium hydroxide here. And we've had 2 things flip places, so when 2 things have moved places, we have what? Double replacement. Okay, and then sodium chloride gets broken apart. So when we start with one thing and we break it apart, we are decomposing it. So decomposition. You throw your eggshells in the garden and they break apart into nutrients. Okay, so they're decomposing. Make sure that you know all of these and what to look for. Right? So one of the other things we talked about a lot is chemical changes. How did we know we had chemical changes? Typically there's a change in what?
Color.
Change in color. What else?
Production of a solid.
Production of a solid. So a precipitate has been formed, and
Gas produced?
a gas can be produced. So great, we already have 3 different ways that we know that we can have a chemical change. We can also have a chemical change because we have felt heat. Remember I brought those packets and the hot hands packets? So heat is produced, and we, with a change in color also, it could be a change in light. So we talked about 3 different forms at the end, and I said it could be heat, it could be light, and it could also be sound. Okay? So how do we get those things in the first place? It's from energy. And as you read in your book this week, a lot of times, or all the time, a reaction requires energy to get started. So if I have my bottle here, and I have my textbook here, Andrew, come blow on the bottle. Okay, Ben, come blow on the book. Okay. What happened to the bottle?
Sorry, blow.
It fell over and like it even like moves a significant amount, okay? Did anything happen to the book? Okay. So with reactions, sometimes they require a different amount of things to make it happen. Now, had I asked Andrew to swipe the bottle, probably would have gone to the wall, right? And had I asked Ben to swipe the book, would the book have fallen over? Yeah, it would have fallen over when he hit it because it required more force, right? It required enough to start it. So as we are looking, we have energy that needs to be exerted to start something and make a reaction happen. So where did that energy come from? For the bottle, where did the energy come from? Came from Andrew. For the book, where did the energy come from? Ben. Came from Ben. It had to come somewhere. Did they just show up out of nowhere? Did I just go, poof, I need an Andrew? No, he already existed. He just moved from his seat and applied the energy he already had, the breath in his lungs, to something else. Ben moved from his seat, applied the energy he already had to the book. So we don't get to make or destroy energy. We just get to take it from somewhere else and apply it to maybe a reaction that we want to happen. Okay? So where does that energy come from when we're talking about chemical equations? Okay? So we have chemical energy. When we see this equation, we have chemical energy that is stored inside each of these molecules. It actually holds it together. So when we look at C3H8, if we were to be able to look at all of the bonds, we're actually looking at this like little beehive thing. Okay? So there is energy in all of those bonds that actually hold the different elements together. Okay? When we're looking at oxygen, remember we also learned we have single bonds. What were these called? Remember that from the last one? We had single bonds and guess.
Double bonds?
Double bonds. And then if we had something that was held together with three, it would be a
Triple bond.
a triple bond. Excellent. Taking notes would benefit you guys. Okay? So, we've got different types of bonds. Different types of bonds hold different amounts of energy in them. And so we've got this energy in here. So in this case, we have our carbon and hydrogen and our oxygen is combining. What type of reaction is this?
Combustion.
Combustion. We've got oxygen and we produce water. And as it goes through, it lets off heat. So we have on the left side, the very first things that we're working with are these are our reactants. Okay? They're what is doing the reacting. Then on the right side, we have our products. It's what's made, right? A product is what you buy at a store. It means they've taken all of the little plastic pieces and put it together, right? So we have our reactants. They start it. We've got our products. And then we ended up with some heat. Heat and anything with energy will always be measured in joules. It will be a J. Okay? Joules. And typically you will see KJ because it's kilojoules. Because it's really inconvenient to write a really large number because most of the time it's in thousands of it, and so I don't want to write 10,000 joules. I'm just going to write 10 kilojoules instead. So when you have a reaction and it goes across and it has produced something that has kilojoules, we have some energy. We are seeing visual effects of the energy that is in there, okay? So then when we talk about activation energy, just like we had with the bottle and the book, which one required more activation energy? The book. It required more to actually get it started. The bottle didn't require very much. So different reactions require a different amount of activation energy. All right, so I do want to go over this one right here because initially we know we've got this. This is not a balanced equation, right? So since we already have this up here, let's see what we really need to take these reactants and turn them into our products. Okay, so I started with my little chart. On the left side, I've got 3 carbons, 8 hydrogens, and 2 oxygens. On the right side, I have 1 carbon, 2 hydrogens, and 3 oxygens. Okay, so the first one where I see there's a big, huge discrepancy is between an 8 and a 2. Can I make a 2 into an 8? How do I do that? How do I turn?
4.
Times 4. Okay, so up here where I have my hydrogen, I'm going to times it times 4 in the front. Okay, so now what do I have? I still have 1 carbon. I now have 8 hydrogen, and how many oxygens do I have total? 2 here and 4 there.
12. 6.
6. 4 times 1 gives me 4 oxygens in the water, and then 2 there. So I've got 6. Okay, so those are my new numbers, 1, 8, and 6. Well, my 8s match. Okay, my oxygen is off, and my carbon is off. Okay, so let's pick either one of those. Or let's stay on the right side. Can I turn my 1 into a 3? How do I do that?
3 and 1.
Yep, times 3. So I'm going to multiply this times 3. So now my new numbers are 3 carbon. Oh, now it changed my oxygen. Again, I have 6 oxygens and 4 oxygens. So instead of 6, I now have 10. Well, my carbons match, my hydrogens match. Oxygen on the left side, I have 2. How do I make 2 into 10?
5 by 5.
Times 5, right? So I'm going to multiply times 5. So now we have a balanced equation. So if I have these amount of reactants, I get this amount of products. So I just added coefficients. We have been calling these coefficients, correct? They go in front. Do they change the amount of the elements actually in that molecule? No. It just tells me how many of the whole group. So if in this case, if this was a pie, our O2, we've put all the ingredients in, we have 1 pie. Now we have 5 pies.
So if you only had 1 oxygen, would that just mean that the reaction just wouldn't take place?
In this one?
Yes, because otherwise it wouldn't be balanced.
Correct, or you wouldn't get, yes, you wouldn't be able to get those.
Okay, so
It has to have 5 oxygens to start reacting with the carbon and hydrogen on this side. Correct. So that was a good thing that he pointed out, because we started out baseline, right, with no coefficients, just trying to get these products. This lowest level that we can get to requires that you have at least 5 oxygen to even start getting reactants on the left-hand side. Okay, so I've added these coefficients. They tell me the number of that whole molecule that we have. There's a special number for these. It is called a name. It's called moles. Okay, I like to think about it as the word amount. My coefficients give me the amount of something that I have. When I have an amount of something, it is measured in moles. Okay, so the M's go together. And the number for moles?
6.02 times 10 to the 23rd power.
Yes. 6.02 times 10 to the 23rd. Okay, is a mole. This is called Avogadro's number. They were measuring like how much of something in 1 unit, so that's the amount of actual particles. So when we're looking at all the particles, we're not looking at the elements, all the particles that are involved in a whole thing. 6.02 times 10 to the 23rd, we're not going to write out all those different zeros. That is a mole. A mole, this whole 6.02 times 10 to the 23rd, is another name for that coefficient. We simply replace it. So here I have 1 mole of my carbon and hydrogen molecule. How many moles of oxygen do I have? 5 moles of oxygen, and it produces how much carbon dioxide? 3 moles of carbon dioxide and 4 moles of water. Good answer. There you go. Okay? So we are simply renaming things that we already know. We're taking our coefficients, and instead of calling them coefficients, we're calling them moles. Okay? Instead of saying it produced some energy, we now know that our energy is measured in joules. We might see kilojoules for that. All right? So, when we have our bonds that are here, our energy tells us how strong that bond is. Okay? So, if who has little siblings? Okay? If you're holding your sibling's hand and you're going somewhere and your mom wants to break that, if they start pulling away, can they pull away pretty easily? It depends on how hard they want to hold on, right? Now, compare it if you and your dad are holding on. So say you've tripped and you're falling and you're falling into a hole. Do you want your sibling to be holding on to you, or do you want your dad to be holding on to you?
Probably my dad.
Probably your dad, right? That's going to be stronger. So your dad is going to have a stronger grip on you than your sibling is going to have a grip on you. So in the same way, every time we bond 2 different things together, it depends on what has been bonded, determines the strength of that bond. So if I'm bonding you and your dad, you're going to have a stronger bond than maybe you and your sibling for it. So as the elements bond, they each have their own amount of energy that bonds them together. Okay? So as it's been bonded, because we know, as we did here, that we didn't just poof and make an Andrew out of nowhere, and that Ben just didn't show up out of nothing, that it had to come from somewhere. Energy is neither created nor destroyed. It's always moving. In the beginning, when God created, He created it all. It was enough. Everything that we ever needed was completely made and created. And so it's just, there's no more new creation. It says that there will be a new creation with the new heaven and the new earth, but currently everything that's created has been done. So we're just moving energy from one place to another in a different form. So the thing that's important about that is that as we move this energy around, when Andrew blows out his breath, is that breath still in him? No. What is it called? Everyone take a deep breath. Okay, breathe it out. What is that called?
Exhale.
Exhale. Okay? Exhale. What word? We've got this X right there. Exit sign. Okay? Exo comes from the Latin root meaning outside, outer, or external. We exhale. We let things out. In chemical reactions, when they exhale energy and they let energy out, it is an exothermic reaction. All right? See how that's going together? So that means we started with something. We started with breath in our lungs. Our body's using it up. We're going to exhale carbon dioxide. We're going to move the wind. We're ending with products on the other end. we have moved stuff out. We have something extra. I like to do it in that way too. You have something extra. We have all those different X's to remind us that that is an exothermic. We are producing something else on the backside. Okay? So, if we've all breathed out and then we breathe in, we inhale. We happen to write that with an I-N. What if we wrote it with an E-N? Okay? To inhale says the prefix END, or endo means within. If you had an endocrinologist, they're going to take care of the insides of your body. So within, inside, or internal, we are looking at endo. We're looking at something in and inhale. So if this reaction needs to inhale some energy to make it happen, where do we get our oxygen, our air and our breath to inhale?
Our surroundings.
From our surroundings. Excellent, Ben. So in the same way, we have a reaction. It needs to inhale from its surroundings, absorb it within itself to make it function. When we inhale it, we're going to need to have some added energy on the front end, correct? So it's absorbing it from its surroundings, and then we would have our products on the back end. So we always have to have our reactions plus that extra energy that it's absorbing, and then we'll get to our products. If you see it on a graph, exothermic reactions look like this. We are letting off some steam. You know, that's interesting to think about it that way. We start with some reactions, we're letting off some stuff, and we end up with our products. Okay? In your book, it talked about the little hump there, and it says the hump represents that little bit of extra energy required to start that reaction, right? So in this, we needed a little bit of energy to start it, pushing over. We need a little bit of energy to push over. We need more energy here. So if I was graphing the energy change for that bottle, it might be like that, right? If I'm graphing the energy change and what is needed for the book, it might look like that. We're going to need a lot more initial energy to get started. Okay? That is called our activation energy. It makes action happen. Okay? We can act if you're activated in that way. Okay? So then for endothermic, it's going to start low, and it has to inhale some energy to get started. So we're starting with reactants, we're inhaling energy, we're adding it, and then we're ending up with the products. And the difference shows us the energy absorbed by the reaction. So everyone have any questions about exothermic, endothermic, and where reactions are headed that way? Okay, we're going to go ahead and head over and get started on our lab now. And then afterwards, if we have time, we will go over stuff for the tests.